Okay, for people joining this meeting, we are looking at things to do with machine learning and the calibration of probabilities. So let's start off with the idea.
This I think we saw last time. Maybe we should go directly to the third section in the diagram, and maybe I can re-explain with the diagram. I remember we went on a bad route last time for the explanations. So basically, the idea of this diagram is that, so on the x-axis, you have the predicted probability, and on the y-axis, you have the actual probabilities. This means that if you take, let's take the one where the x-axis is 0.1, it means if I take everything that I predicted with 10% of chance, everything that the classifier on a test set predicted with 10% of chance, and look at all of them, and I counted how many times the prediction was true, and it was true only 1% of the time. So that's kind of what this thing means. You take every time you see a 10% probability in any context, like it doesn't matter if the 10% was a top probability or not the top probability, just anytime there's 10%. And there's a little bin, of course, because it's never exactly 10%. So it's among the prediction that were around 10%.
I'm just very surprised that the mapping is, everything around 10% ends up being 1%. That isn't just a big spread. Or what does the...
It is. Okay. So that's, I mean...
Why are the error bars so small here?
It's because of the number of... so this is just the standard error. I mean, actually, it's more complex than that, but whatever. It's because there's enough example in the bin to have a small error bar. So we don't care about the spread, actually, because it's either 1 or 0, right? It's each example is either the prediction is correct. I mean, in that case, it's not correct because it's just 10%. So there could be something else at 30%. But anyway, either it's realized. So you predict 10% of cat. So either it is a cat or it's not a cat. So it's just a bunch of 1 and 0. And you compute the average of that. So it's an average. And so average is 0.01. And with the standard deviation that I showed here, because we have a finite test size. If you were a test set that was, millions of examples, you would have no error bars. And actually, one of the things that I spend a lot of time on is to appropriately choose the number of bins, like in automatic histogram, because you want to kind of balance the number of bins with the errors in each bins. If you have few bins, you have big errors, but you only have few bins, so poor resolution. But if you have a lot of bins, then you can have less example in each bin, and so you have large errors.
Okay, let me try this again, trying to understand what you're doing here.
Yeah.
Okay, so the classifier says it's a dog. It says there's a 0.1% probability that it's a dog.
For example.
Okay. And now we look at the training set and we say...
Test set.
And we say, you said that there's a 0.1% probability of these 100 pictures. You said that you implied that 10 of them were dogs. Okay. But actually, only one of them is a dog. That's what you're saying here. Is that correct?
Not exactly, because I mix all the classes. It's just I take, anytime you say 10% of chance for something.
All right. Okay. Fine.
I put them together.
Let's ask the question. There's a different measure which says for a dog specifically.
Yeah.
And what you're saying is you're taking all the things that are predicted probability around 0.1, and there may be things with 0.99, 0.12, et cetera, et cetera, et cetera.
Yeah.
Those are all being binned.
Yes.
You are auto-binning in some way.
Yeah.
Right? So you're saying that Okay. So you're saying for the things that were those probabilities, everything that had about that probability, look at how often it actually showed up.
Exactly. Exactly.
Okay. Okay. So now what do we expect? I mean, I understand what this curve is. I understand what that line is. I understand all of that. So what are you going to do with this result, other than just look at it and say it's good, it's bad?
So, well, for classify, the calibration is internal. So if you see that it's bad, you can retrain and setting calibration to true, which currently is a hidden option, but we could think of making it a top level option. Otherwise, it's mainly,
All right. So you are retweaking it.
Actually,
you have a go ahead.
Yeah. Actually, so sorry. In the general case, somebody gives you a classifier and you see it's badly calibrated. What you do is that you train a model to calibrate it. I mean, okay, or you could change your training procedure. So let's say it's a neural network and you see it's badly calibrated. So for classify, it's kind of automatic calibration, right? But if it's a neural network and you see if it's badly calibrated, you could either go back to your training procedure and understand why it's badly calibrated. Maybe you are overfitting in some way. Maybe your way to prevent overfitting, you were looking at the wrong metric. You were looking at accuracy where you should have been looking at the likelihood or something like that.
Mm-hmm.
Or you do a post-processing, which is just a little model that takes the probabilities as input and return new probabilities as output. So it's kind of correcting the probabilities.
Yeah, I understand. Sounds exceptionally dangerous, but no more dangerous than a lot of what people do in machine learning.
Yeah.
I mean, it's one of those things where it's like, we got it wrong, but we're going to hack it. I mean, it's very much like it's in the my crocodile ate my homework type, or I don't know what it is. It's a very
yeah. I completely agree that I mean, I'm not 100% sure on this topic, but I feel that when a neural network is badly calibrated, which apparently most modern neural network, for example, trained on images, are badly calibrated. And I believe that there's something wrong. I believe that it's
well, I'm always surprised when we look at the probabilities for it's very, very certain that it's a snake, for example, and it's
exactly
too certain that it's a snake.
Exactly. Well, that's a problem of calibration, and that's typically they are overconfident. Yeah, neural networks trained on images, modern neural network trained on images, in the classic way, are typically overconfident. So they look more like not this one. Yeah, they look like that one.
Okay, so let's talk about the names for these things. Okay.
No, actually, the other one. Sorry, they look like the other one.
What is the difference between this?
So this one is underconfident. This is the same.
No. But I mean, these pictures here: reliability diagram and classic reliability diagram. What's the difference?
Yeah. So they are the same data. Is just the scaling that is different. The scaling function.
Okay.
One is a logic scaling, and everybody does this classic thing. That's why I call it classic. But I think people should the one that has a logic scale, because you can see things that are near 0 and near 1.
Yes.
And you see it's a nice straight line. Otherwise, it's like this weird S curve. Yeah.
Well, it's interesting that it's a straight line. Is it obvious why it's a straight line?
No. It could be anything. But as it happens, it often.
What does this look like if you do it on our image identification network? What does this look like?
I didn't do that, but I'm pretty confident that it would be overconfident. So
right.
So it would look like on the opposite, like the symmetric with respect to the diagonal. This is an underconfident one. Actually, yeah, that's why it's often line. Is because typically it's a matter of overconfidence, underconfidence. In a general sense, it could be anything. You couldn't say it's over, yeah.
But why on a logic scale should it be a straight line? That's what I'm asking.
Yeah. I don't know exactly, but that's good for us to change it, because the model to calibrate, you just change the what we call the temperature of the probability distribution. It's called temperature scaling. So basically, you just multiply the log of the probabilities by a number, and then you do a softmax again, and this is enough to calibrate most models. So extremely simple calibration model, and works pretty well. So that's what we have implemented currently in Classify. But arguably, you could use other model to calibrate.
Look, I think this should be called something like probability recalibration arrow true or false.
One thing, though, I realize we could make it a little bit more generic with predict. So it doesn't really make sense for predict to calibrating the probabilities.
Yeah, I understand, but isn't that a different operation, calibrating the values, recalibrating
exactly,
the values?
Exactly. It's more about calibrating the values. It's more about a post-processing function, really. And in a sense, this calibration, okay, my idea was, following the rule that, Roger told me a few times, that option that are true or false are generally bad design. So, can we make a sort of calibrator function, or probability calibrator, and then the user can also have a custom model and they put it in. And for classified, this function would take an association of probabilities. I think that's the only way to do, and return a new association of probabilities. But for predict, it would just take a value and return a value. It would be stupid to do something else, because that's, like you won't give a distribution. It doesn't make sense. It could make sense, but simpler to think in putting a function rather than a.
So why not a recalibration function?
Yeah, that could be something like that. Yeah.
And then,
I was thinking maybe we should follow, because we have feature extractor and we have anomaly detector. So maybe it should be just by consistency to have something end in or, even though it's sometimes not very pretty.
I don't think it's a good idea in this case. I think it's a recalibration function, because I don't think that unless
distance function.
Yeah, right. Okay, so here, it would be something like probability calibration diagram.
Yeah, that's
probability calibration data.
Yeah, the two standard name is either reliability diagram or calibration curve. That's the two standard name. That's why in the title, in the plot label, I put, parentheses calibration curve. But
I don't think you should call it that. I think you should just call it probability calibration.
Okay, yeah, this I can do.
Diagram of probability calibration curve would be okay, I think. I don't think reliability is the right thing. Reliability is like, we're reliable, but it's just, it's far away from that concept.
Yeah. That in statistics they call it like this.
Yeah, well, they call a lot of things strange names in statistics. It doesn't help that it's mostly 100 years old.
Probability calibration. Yeah. Sorry.
No, go ahead.
Yeah.
Okay, and I think this notion, I like actual probability. Well, if it's the probability in the test set, why not say actual probability in test set?
Mm-hmm.
Predicted probability in
frequency in test set, or test set.
No, okay, that's better. Actual frequency in test set.
Mm-hmm. Okay.
Actual frequency would be good. Just predicted probability, actual frequency.
Yeah, it makes it a bit clearer. Otherwise, like what? The test set has no probability.
Right. So, Ren on our live stream is asking, how are we defining actual probability? Yeah, if you have an image of a cat, it either is a cat or it isn't a cat. Yes, exactly.
Exactly.
Unless it's one of those, never mind. I'm thinking of all the variant, pseudo cats. Okay, so then we'd say actual frequency, predicted probability, actual frequency here. And at the top it would say probability calibration diagram. Actually, why are we giving a title at the top? Do we need a title?
No.
Okay.
I thought it would be nice to.
Well, it's not clear that it helps. I mean, if you're saying predicted probability and actual frequency, that's kind of telling you what it is.
For someone that knows, yes, but.
Well, but it's not helping you to say probability calibration. All right, well, probability calibration diagram at the top wouldn't be bad. Okay, so then I would not label it. I don't see the point. I mean, it's clear what that line is.
This side, I think it's nice to remind, and people can always select it like it's legended, so if they really want to put in their report, they remove that pretty easily.
How do they remove it?
Well, you just click on the left and copy paste, for example. Yeah.
Oh, I see.
This is fairly well contained. I don't know. I like to explain a bit. I think a lot of, especially this concept, is a bit elusive to some, and.
Well, yes, we spent an hour talking about it.
So, I do the same for this comparison plot. You have a sort of that on the x-axis it's for predict. It's the value, the predicted value, and on the y-axis it's actual value. And so you have a scatter plot, right? And so I put a line as well, and it's like perfect prediction line or something like that.
All right, okay. Well, you could leave off the word line. You could just say perfect calibration.
Yeah, it's true. Yeah, definitely.
Okay, so then this would be probability calibration diagram, and you could say classic probability or linear probability calibration diagram, or classic, whatever you want. I wouldn't call it classic because it's only classic today. The Etienne one may become classic in the future.
I actually hope so. I think it's wrong. I think it's wrong, this linear thing.
Well, fine. So then say linear probability calibration diagram.
Yeah.
With the other one.
Yeah, okay.
Okay, so then here we probability calibration data. What is this anyway?
It's the data of the curve, that's it. Which many people would like, then they can do really, the plot they want.
Fine. All right. And this would be a recalibration function arrow, automatic or true or whatever it is down here.
Yeah, that's and that would be a symbol.
Yep. Okay. Does this do it?
Yeah, I think that's it. And on the bottom, you can see, we already discussed about it, but basically that would be the way this function would work. That it would take an association of probability and return the association of probability, and or a value and return a value for predict.
Sorry, what are you saying here?
So this calibration function would work like that for classify, and for predict, it would just take the value and return a new value. Like that would be its spec. If someone
I'm thinking.
Oh, actually, no, sorry. It would take log probability.
Why isn't it just taking a probability? Why isn't the classifier?
Because then it could produce a probability that is not valid. Where if it's log, I always do a softmax. It's kind of the natural.
Wait. Okay. I thought this function was just going to take a number, 0.1, and going to return another number, 0.01 or something. I didn't think it was going to know anything about the classes anymore.
Yes. Okay. I forgot to mention that. So my definition of calibration is a little bit, reducing, simplified. The true definition is more general, and you cannot represent it in the diagram because it's multidimensional. It's among all the examples that have P1 for class 1, P2 for class 2, P3 for class 3, and so on. Among all these examples, and of course you need to have a big test set if you take this definition. You bin the example that are near these values of probabilities, and then you look at the realization. One is the frequency of class 1, frequency of class 2, frequency of class 3. That's kind of a more generic.
Yeah, I understand.
Definition. Yeah.
That hasn't squashed you down to just saying there's a certain probability. It's saying, where do the probabilities come from? I mean, here you're taking what we discussed before. You're taking all things,
exactly,
dogs, lizards, whatever, that had a predicted probability of around 0.1.
Yeah. So it's a weaker definition,
right.
But that's allowed to visualize it. And often it's, I think it's
okay. But you want both things, right? You want the possibility of having just a pure probability changer, as well as the possibility of having a probability changer by class.
I think the more generic thing is honestly, you rarely. I think the more generic one is enough.
Wait a second. What you would be doing here is simply taking this curve and twisting it, right? You're just going to have some function. That's what you did here, right? Took that curve to get that calibrated thing. You took that curve and you just mapped 0.99 to whatever that it is down there, right?
Actually, no. The way it's trained is it's keeping in the original n-dimensional space, so to speak. It's learning a model. So let's say there's n class, so there's n probability. It's learning a function, input n to n.
Okay, I'm lost because I thought what we were doing was we have probabilities that we get out, right?
Yes.
That have been already aggregated across. I mean, it's a weird thing to do, but all things, dogs, crocodiles, teacups, they all have, probability 0.1. And those are the things that enter that bin there, the probability 0.1 bin, right?
Yes.
Okay. Yes. So now, one thing you can do is to say everything with probability around 0.1 or probability around 0.5 or something should be remapped to being something with probability around something else.
Yes. Okay. Since we use a simple model, that's basically what we're doing. There's but
okay, but in general, it could depend on the class, right? If you knew the class, because your recalibration function then is basically a post-processor, a general post-processor that's taking from that class. But this isn't even right. I mean, this isn't even right because it's a function, right? Given a probability P1 that is 0.726, you're then returning for that class, the probability should be something else, right?
Yes, but you have to know that the probability have to be normalized, right? So it needs to be renormalized in the end. That's what you cannot really change one probability on its own.
Look, it doesn't make any sense. It doesn't make sense. Your classifier just gave you a certain probability for the class of elephants.
Yeah.
Okay, but this thing that you gave here, this. Oh, I see what you're saying. You're saying you specify what probabilities you're giving for all those classes.
Yeah.
And then this gives you what? Okay, fine. But you can, in fact, do, okay, so the simpler cases, you just take the calibration diagram and you simply apply a function to the values in the calibration diagram to give new values, right? That's the simplest case. And that's the analog of this case here. Yes, because in this case here, the analog of doing this would be to say, give the input.
And do renormalization. You can have a function that takes indeed a probability. Independently, it takes each probability, transform them.
Right.
And then you have to renormalize.
Absolutely.
The probability
Well,
needs
actually, I
sum
don't
to
think
1.
you do have to renormalize, because the truth is that, for many purposes, it's just, oh, you said it was probability 0.9. I'm going to say it's actually probability 0.7. The global normalization of that is irrelevant.
Yeah, but I mean, it's kind of a contract we have when you have a classifier. It gives you a probability of over the possible classes, a valid distribution over the possible classes.
Fine. So then you might have to renormalize. Okay,
yeah.
but I mean, this. Okay, so you've got two cases. Either the recalibration function takes a value, a probability value, or an output value in the case of predict, and returns a new value, or it takes a richer set of things, which in the case of prediction would be not the analog of this would be if you've got a predictor, pred, that takes X and returns Y, okay? Then what you do for the recalibration function is the analog of this would be to say, give me both X and Y, and I will give you back, Y prime, basically. See what I'm saying? Because that's the analog of saying, well, what class was it in?
No, you don't give X here.
No, you do. If you're going the analog of this case, you give X, because otherwise you're just saying the value I got was Y, so renormalize Y.
Yes, exactly.
Right, but I'm saying that you're saying the value I got for a particular class was P1, and I'm giving you the class P1. I'm not just telling you the value you got was P1. So I'm saying the analog for the predictor of this form, right? We've got two forms, right? We've got the pure numerical renormalization, okay, and then we've got the context dependent renormalization.
But okay, in the classifier you don't give the input. Right. So it's just two different beasts. The classifier gives a vector of probabilities, and predict gives a distribution of numeric values. So okay, the full analog would be that you give the distribution of a Y to the calibrator. Right. One is a distribution on the categorical space. The other one a prediction on numeric space. But giving a distribution to the calibrator,
it's a big can of worms.
It's a big can of worms. It's much easier to work with a value, and in the end, you can still transform distributions by defining a function. So it means that if you query the distribution, it's going to be the transformed distribution by this calibrator, and that's fine, I think.
I don't see how any mere mortal is going to write a recalibration function.
It's I
think it's sort of pointless to offer it. I mean, look, you can have recalibration function arrow automatic or none, and that's fine. But what it does in this case seems to me difficult. And it might make more sense if you were to just give, given a probability, how should it be renormalized? Or maybe what you feed to the recalibration function is some kind of complicated association that can have a bunch of things in it where it can pick out what it needs.
You can be a bit smart by having all the probabilities. It's true that many methods, they just focus on single probabilities, modify them a bit independently, and then renormalizing. But you can be a bit smart. Especially if you have a large calibration set, let's call it, you can start having models that are a little bit smarter. And
But under what circumstances the recalibration function is called only once? Is that a true statement, or is it called on every piece of I? When is the recalibration?
Only once on the output probability, all the vector probabilities, or this association of probabilities, and you give the new association of probabilities.
Except sometimes you just want it to be a function that is just saying, some function of a single piece of I. Making sense? I mean, right. So you've got two cases. You've got the case where you want to give the whole thing, and you've got the case where you just want to give one of them.
Yeah. Except, of course, when you have the whole thing, you have the one of them as well. So, the association, if I want, like the classic one is just this temperature scaling is just a power. Like you take this probability, you do power 0.5, and then you renormalize.
Okay. Well, but fine. But then that should be the recalibration function arrow square root.
And actually, yes, that's pretty good. Something like that, it allows you to change the temperature directly, and that's super classic. You can do it by hand. This is good. These people will use that.
Fine, but I mean, but then, okay. So the problem is, if you give recalibration function arrow a function here, right? The question is, how do you have an escape valve that allows the system to feed in this whole giant vector, whole giant association? You want both cases. You want both the case where you're being fed in piece of eyes and the case where you're being fed in the whole association, right?
I think this SQRT will work on the association, right? So
well, it will actually, yes.
Yeah, so it means that we are good. I think most
yes. All right, yeah. Fair enough. I see what you're saying. So your basic claim is, if I take this association here, and I've made a function, so if I say square root of that association,
yeah, because they are, because they are listable, it will work. Of course, if you do a custom function that works on only one value, it won't work. But I think in 90% of cases where you just use functions like that, it will just work.
Fine. That's nice. All right. And automatic will involve you doing whatever.
Yeah, some methods are calibrated, some methods are not. And yeah. Oh, there's one thing I don't know in that. How could we specify, please calibrate everything?
What do you mean by calibrate everything?
Like we have the calibrate none, right? I mean, recalibration function goes to none. Recalibration function goes to automatic. And what would be the case for?
Well, what is recalibrate everything? What does that mean?
So it means there's a bunch of methods. And in automatic, for example, random forest is going to be recalibrated. Gradient boosted tree is not, because it's already calibrated.
So we just say recalibration function arrow all and have it do everything.
Oh, yeah. Exactly. Automatic, none, all function.
Okay.
I think it's good. The square root, like it's a temperature scaling. People might like to do it just by hand by saying, oh, it feels a little bit too big peak in my distribution. Let's just smooth the distribution a little bit. And
let's see. Ethan is commenting, why, when you do inference, you need to be able to change the temperature manually.
Well, that's what it is. That's what it is. Yeah. In some models like this, GPTs, so these language models, they offer a way for you to change the temperature of the distribution of next characters. And so you can create something that is a bit more, exploratory, or something that is a little bit more predict, the most likely character.
Right.
Because there's this famous example of this language model trained on Wikipedia. And if you put a temperature of 0, it does something like the United States of the United States of the United States of the United States.
Huh.
Because it's the most likely thing, but it's not really, typical.
So Ethan says, in general, it should be automatically optimized with grid search.
Well, that's what's happening in Classify. Like the calibration is basically a model that is trained to calibrate as good as possible.
Fair enough.
And it works pretty well. Like if you scroll up, like I was so surprised. This let's say the
Great.
random
So,
forest.
sorry. This is for Devon. This is some kind of crazy error. Can you screen cap that, please?
Yep. Yeah, I just got it.
It means you're not getting this email. But okay. Okay, sorry. Random forest. Yep.
Oh, no, I was just saying, like, to cheer up a little bit. If you scroll up, like the first example, yeah. So that's this. You've seen it, like this diagram where it's not calibrated at all.
Mm-hmm.
It's completely underconfident. And if you scroll down a bit,
yeah, I saw you can calibrate it.
And so that's a new now in
this
classify. When you use classify, that's what happens now. And
great. What does it do to image identify? Does it make image identify more sensible?
We haven't calibrated it, so that would be for the next version of image identify. That would be really great if we calibrate it. I think, definitely we should. And okay. I think we should train a new one soon, because now there are some models that are quite better, so we should use them.
Fine. All right. Sounds good. This was easy, he says.
Cool. Yep.
This is the moment where people say, and there's just one last thing, and that turns out not to be easy at all. Do you need this file, or can I just get rid of it?
I think, yeah, that would be good. Although, I mean, it's all recorded.
Fine. I will store
Sorry.
it. No problem. What is it under? You're on that framework, calibration meeting 2. Great. Okay, sounds good. All right. Well, thanks everyone. Thanks to folks on the live stream. I think there's another live stream for people who are interested. There is another one coming up in about an hour and a half. So talk to you all soon. Okay. Bye-bye.